Welcome to a deep dive into the fascinating world of the Kolakowski sequence.
Oh, this is a fun one.
Yeah, it's deceptively simple, a string of ones and twos, but...
It's one of those things that, you look at and you think, oh, okay, ones and twos, what's the big deal?
Right.
But it's puzzled mathematicians for decades, this thing.
It has, and that's why we're doing a deep dive on it today.
Absolutely.
So what's fascinating about this is that it kind of emerges from itself. It's like almost like a mathematical fractal.
Yeah, it encodes its own representation. It's really quite elegant when you get down to it.
We'll be drawing from two comprehensive resources on integer sequences for this deep dive. The Online Encyclopedia of Integer Sequences, OEIS, specifically entry A000002.
Right, the OG.
And the Wikipedia article on the Kolakowski sequence.
Two fantastic sources, though I will say they can be a little dense.
They are very dense, but don't worry, we've got you covered. We will be extracting the most interesting nuggets and insights so you can understand this unique mathematical puzzle.
Exactly. We'll break down what makes the Kolakowski sequence tick, why it has mathematicians scratching their heads, and maybe even inspire you to uncover some of its secrets yourself.
So let's jump right in. Imagine a line of ones and twos stretching out infinitely. 1, 2, 2, 1, 1, 2, 1, 2, 2, 1, and so on. That's the Kolakowski sequence.
And the real beauty of it, the real beauty lies in how those ones and twos are arranged. It's not random. There's a surprisingly simple rule that governs the whole thing.
Yeah. Each number actually tells you the length of the next group of alternating digits. So that first one means a single 2 follows.
Right.
Then that 2 signals 2 ones are up next. And this pattern continues, creating this intricate dance of ones and twos.
That's like a little mathematical conga line.
And here's where the self-generating aspect comes in, right? This rule isn't just a one-way street. You can apply it backwards, too.
Exactly.
So each number also represents the length of the previous run of numbers. It's like the sequence is weaving itself into existence.
Guided by this elegant, symmetrical rule, and that's what makes it so fascinating. You can go forwards or backwards, and it still works.
So the sequence is its own blueprint.
In a way, yeah.
Like a mathematical self-portrait. We'll be sure to link to an animated GIF from the Wikipedia article in the show notes. It shows how the sequence grows, block by block, based on this run-length rule. Seeing it in action makes the concept a lot clearer.
Oh, yeah. It's mesmerizing to watch. You can really see how it builds upon itself.
You know, it kind of reminds me of musical notation. The ones and twos are like the rhythm, the duration of each note.
You can think of it that way. Absolutely. It's creating a kind of mathematical melody.
I love that analogy. You could even use this pattern to create art, where the length of each line or shapes is determined by the Kolakowski sequence. Suddenly you have this visually intriguing piece based purely on this mathematical concept.
Absolutely. It just goes to show that even these seemingly abstract mathematical concepts can have surprising applications in other fields. But, this is just the tip of the iceberg. This seemingly simple sequence, it's for profound mathematical mysteries beneath the surface, mysteries that to this day remain unsolved. Unsolved. Buckle up.
We're back, and I gotta say, I'm ready to dive deeper into this Kolakowski sequence. So it's cool, it's elegant, but there's some big question marks around it, too.
Yeah, big ones. The unsolved mystery of the Kolakowski sequence, it's this. Do the ones and twos in this sequence, do they show up with equal frequency?
Okay, so when you say frequency...
Like how often does a 1 pop up compared to how long the sequence is? Mathematically, we're talking about density. Is the density of 1s equal to 12? Okay,
so by density, we mean, like if you looked at the first, say, 100 terms of the Kolakowski sequence.
Right, take a snapshot.
And you counted up 50 ones.
Yeah.
The density of 1s would be 50 over 100, which would be 12.
Exactly. The question is, does that hold true for the entire infinite sequence?
It seems intuitive, right?
Yeah.
Given how it's built, like that could be right.
You'd think so. But proving it mathematically, that's a whole other story.
So no one's been able to definitively say, yep, 1s and 2s, they show up the same amount, even though it seems like it should be true.
It's like this sequence is taunting mathematicians, like, you think you know me.
Right. It's like, come on, figure me out.
Exactly. But even though there's no full-blown proof yet, that doesn't mean mathematicians have been sitting around twiddling their thumbs,
No, of course not. People love a good puzzle.
Exactly. There have been some pretty significant steps forward.
Like, our sources mention these mathematicians, Schwadel and Nielsen. They used some pretty intense math to get closer to an answer.
They did. They established what we call upper density bounds.
Okay, so what does that mean? Upper density bounds.
So Schwadel, he was able to prove that the upper density of 1s, it can't be greater than 0.50084, he put a cap on how often those ones can appear.
Which is really close to 12.
Yeah.
But not quite there.
Agonizingly close. But then Nielsen comes along and tightens the noose even further. Using even more powerful tools, he shows that the upper density of ones is actually less than 0.500080.
Wow. Getting closer. So saying it's got to be less than this, closer and closer to 0.5.
Exactly. And the computational power needed to even figure that out, we're talking analyzing billions, trillions of terms in the sequence.
That's wild. So, okay, we've got this density question still kind of hanging in the air. But our research also mentioned the Kolakowski sequence and something called tag systems.
Yeah, that's where things get really interesting, but also a bit more complex.
To be honest, that part left me a little lost, I think.
Yeah, tag systems, they're a bit of a brain bender at first. Picture this. Imagine you've got a set of instructions, right? And these instructions are all about rearranging blocks. Each block has a color, and the rules tell you which block to move next, based on what color you see.
Okay, I'm kind of seeing it. Like a more complicated Rubik's Cube, kind of?
In a way, yeah. It's a way of manipulating symbols based on rules, kind of like a super basic computer program.
Oh, okay. And the Kolakowski sequence, it's all about rules too, right? How those ones and twos determine what comes next.
There you go. You're making the connection. Turns out you can actually define the Kolakowski sequence using a specific type of tag system. But here's the kicker. This tag system, it's something we call Turing complete.
Turing complete. That sounds important. Even I know that.
It is. Turing complete means that this tag system, and by extension, our friend the Kolakowski sequence, it can represent any computation a computer can carry out.
Wait, so this sequence, it's not just about ones and twos. It might be as powerful as any computer out there.
It's a mind-blowing concept, isn't it? This string of numbers potentially capable of doing anything your smartphone can do.
That is absolutely wild.
It just goes to show there's a lot more to this sequence than meets the eye.
And it gets even more interesting. The OEIS entry, it mentions something called the Gallum sequence.
Ah, yes. The well-behaved cousin of the Kolakowski sequence.
Oh, how so?
Well, the Gallum sequence is also self-generating, kind of like our friend the Kolakowski sequence. But here's the thing. We understand the Gallum sequence. We've got formulas for it. We know its properties inside and out.
It's like the Gallum sequence went to math school, got straight A's, and the Kolakowski sequence
skipped class and is out there causing a ruckus.
Exactly. But why should we care about any of this?
Yeah.
This is some pretty heavy stuff. We'll be back in a flash to answer that.
And we're back. So we've journeyed through these self-generating patterns, right? We have grappled with unsolved mysteries.
It's been a wild ride.
It has. We've even dipped our toes into this world of tag systems and Turing completeness.
Which, by the way, fascinating stuff.
Absolutely fascinating, but why? Why should we care about any of this? It's cool, but...
Well, I think that's the beauty of exploring these mathematical concepts. It might seem abstract at first, right? But there's a deeper lesson here for all of us. The Kolakowski sequence. It takes these really simple rules.
Ones and twos. Exactly. And from that, it creates this incredible complexity. It's like a mirror almost, reflecting patterns we see everywhere in the natural world.
Like that saying, math is the language of the universe. It really is. You start looking for it and it's everywhere.
Exactly. Take DNA, for example.
Yeah.
Built from just 4 basic building blocks, but those elements, arranged in a sequence, they hold the blueprint for an entire organism.
Incredible when you think about it.
It is. And just like those 4 base pairs in DNA encode the complexity of life itself, the Kolakowski sequence, with its one simple rule, generates this infinitely intricate pattern.
It's like nature showing off a little bit.
A little bit. It's a reminder that amazing complexity can emerge from simple rules. And the Kolakowski sequence, it's not just highlighting the elegance of the universe, it's also kind of revealing the limitations of our own understanding.
How so?
Well, we've got all these sophisticated mathematical tools, powerful computers, and yet this question of density in the Kolakowski sequence, it's still unanswered.
So it's a bit humbling, too. We don't know everything.
Exactly. There's still so much out there to discover, even in the 21st century.
Maybe one of our listeners will be the one to crack the code.
Wouldn't that be something?
It would. And speaking of exploring further, be sure to check out the OEIS and Wikipedia entries. We'll link them in the show notes.
They're treasure troves of information, not just on the Kolakowski sequence, but tons of other fascinating mathematical concepts.
Yeah, go down the rabbit hole a bit.
Yeah.
So that wraps up our deep dive into the Kolakowski sequence.
It's been a pleasure unraveling its mysteries with you.
Always a good time. Keep those minds curious, everyone, because the universe is full of patterns just waiting to be discovered. Until next time.